Today's discussion concerns the minimization of combinational circuits. We have three tools that we'll explore. We'll briefly look at Boolean algebra. We'll spend the bulk of our time dealing with these Karnaugh maps, otherwise known as K-maps, and then, time permitting, we'll briefly look at the Quine-McCluskey method. As we get started, I'd like you to consider two terms. The first is the sum of products. The other is the sum of minterms. Keep in mind that minterms are products. An example is minterm 10 with inputs D, C, B, and A, which serves to remind us that minterms are special. They are special in that the minterm contains each input. With that said, let's shift our attention over here to the left and consider this expression. F is equal to BA or DC0 or DCBA. This expression is a sum of products. So we would say, yes, it is a sum of products. But we would say, no, this is not a sum of minterms. The reason this is not a sum of minterms is because this is not a minterm and this is not a minterm. Only this term, number 15, is a minterm. With a bit of work, we could expand this to be a sum of minterms. The first term becomes x, x, b, a, where x's stand in for the d and c terms, because this particular term here does not care what the values of d and c are. The second term becomes d c0 x, x, because this does not care what values b and a take on. And then the last minterm comes down. As we continue our expansion, we'll see that this first term actually encompasses 4 minterms, including D0, C0, BA, D0, CBA, DC0, BA, and DCBA. Likewise, this term expands to encompass 4 minterms. And the last term comes down. If you have your handy-dandy note card converter at the ready, you can identify these minterms as 3, 7, let's see, 8 plus 2 plus 1, that's 11, 15, 8, 9, 10, and let's see, that's 8 plus 2 plus 1, I believe that's 11, and finally 15. The compact sum of minterms equation includes minterms 3, there's that one there, 7, 8, 9, 10, you'll notice there's 2 11s, that takes care of those, and 15. I think you'll agree that's a relatively straightforward operation. We started with a sum of products equation, and we expanded it so it became a sum of minterms. Right? That's an easy direction to travel. This is an important concept, so let's write this one more time. we start with a sum of products, which is expanded to a sum of minterms equation, something we would go so far as to describe as easy. But what about the other direction? Suppose we have a sum of minterms and we want to find an optimized sum of products. Well, that might not be so easy. Which brings us to the main point of our discussion, and that is to identify the tools that are available to us, including Boolean Algebra, the Karnaugh map, and the Quine-McCluskey algorithms. Remember that circuit minimization is important to us because it determines how the hardware will be built. For example, in this equation, we see a 2-input AND gate, a 2-input AND gate with an inverter, a 4-input AND gate, and then a 3-input OR gate. Not terribly complicated. As opposed to this sum of minterms, which requires 1, 2, 3, 4, 5, 6, 7. That's 7 4-input AND gates. Obviously, this circuit here is much easier to build if we can just find a way to describe it. With all that in mind, let's go back to this piece here. Remember, this was an expansion. Our objective is to go in the opposite direction, to essentially go from all of the minterms to a optimized sum of products equation. Consider this. What is the difference between 0 and 1? For simplicity, let's assume 4 bits. So a 0 would be represented as 0, 0, 0, while the 1 would be represented as 0, 0, 0, 1. And I think you'll agree that the difference between these is 1 single bit. What about 1 and 2? So 1 is 0, 0, 0, 1, while 2 is 0, 0, 1, 0. This can be described as a 2-bit change. So our 1's bit changed and our 2's bit changed. For reasons that'll be clear later, we're going to throw that one out. What is the difference between 1 and 3? So 0, 0, 0, 1 and 0, 0, 1, 1. We see that is a single bit change. 1 and 5, 0, 0, 0, 1 and 0, 1, 0, 1. Once again, we have a single bit change. And the last one is 1 and minterm 9. Once again, single bit. In each case, when we compare the number 1 to these other numbers, there is a single bit change. Now, why do you care? Suppose you had a circuit that responded to minterm 0 and 1. Now, we could certainly build that as 2 4-input AND gates, but it would be nicer if we could somehow combine the terms. And we can. If the circuit responds to both minterm 0 and 1, you could describe the circuit as a 3-input AND gate, as 0, 0, 0, with no sensitivity to A. Likewise, if the circuit was to respond to minterms 1 and 3, you could build the circuit as D0, C0, we don't care about B, and then A. 1 and 5, it would be D0, we don't care what C does, the C, it would be B0 and then A. And finally, if that circuit should respond to minterms 1 and 9, we wouldn't be interested in D, but we would look for conditions where it's C0, B0, and then the last one is A. Okay then, let's make sure we're on the same page by looking at the Boolean algebra for these two minterms. F would be equal to minterm 1, which is expressed as D0, C0, B0, A, and minterm 9, which is expressed as D, C0, B0, A. You'll notice that each minterm contains C0, B0, A. Rewriting the equation, we can actually factor out that C0, B0, A, which leaves us with D0 or D inside the parentheses. So when all is said and done, if our circuit is to respond to minterms 1 and 9, we build C0, B0, A. This is really just a pattern recognition thing. We recognize that there's some relationship between minterms 1 and 9, just like there's some relationship between minterms 1 and 5, and 1 and 3, and 1 and 0. If only we had a way of graphically showing what those relationships are so that we could quickly identify them and quickly simplify the circuit. And it turns out we have such a tool, and it is called the Karnaugh map. It goes something like this. Let's identify the rows with inputs D and C, and the columns with inputs B and A, where BA can take on the values of 0, 0, 0, 1, 1, 1, and 1, 0. And now for the rows, DC can take on the values of 0, 0, 0, 1, 1, 1, or 1, 0. Now we identify each cell by its minterm. So 4 zeros would give us minterm 0. The other simple one is all ones. So that cell would be 15. Here's number 1. Here's 2. So 0, right? This would be 0, 0, 1, 0. This would be 3 as 0, 0, 1, 1. Keeping in mind that as we move across, we are only changing one bit at a time. So from here to here, that's a 1-bit change. From here to here, that's a 1-bit change. And from here to here, it's a single bit change. You might see where we're going here based on this conversation where we were changing 1 bit at a time. But before we do that, let's fill in the rest of the table. In the second row, we have minterms 4, 5, 6, 7. In the last row, it's 8, 9, 10, 11. And then we finish it out with 12, 13, 14, and 15. Remember what we said in this conversation up here. If a function contains minterm 0 and 1, there is a 1-bit difference between the two. If a function contains minterms 0 and 1, there is a 1-bit difference between the two. These two terms can be simplified to D0, that's this one here, C naught, that's this one here, and B naught. The circuit is no longer sensitive to A. And that is exactly what we wrote up here. It is D naught, C naught, B naught, and no longer sensitive to A. Same goes for 1 and 3. That's this one. Together, minterms 1 and 3 become D naught, C naught, and then these two, which is A. Does that look familiar? So D naught, C naught, we're not interested in B, but we are interested in A. Moving back to our K-map, we generalize by saying that there's a 1-bit change between minterms 0 and 1, a single bit changes between minterms 1 and 3, a single bit changes between minterms 1 and 5, and finally a single bit difference between 1 and 9. The same argument could be made for minterm 15. There's a single bit change across those cells, a single bit change between these adjacent cells, here again, and a single bit between 15 and 11. Knowing that, let's go back and look at our original problem, where we described an equation as the compact sum of minterms with terms 3, 7, 8, 9, 10, 11, and 15. We'll write a 1 in the cells corresponding to the minterms, and a 0 in all other cells. Remembering that there's a 1-bit difference between adjacent cells, we can circle cells such as this and describe what the simplified circuit is. So this particular one becomes D naught BA. So D naught BA. We'll circle this, which becomes D, and then it's in the BA column. Here's another. This is in the D C naught row, and then it looks like it's sensitive to B naught. And finally, let's collect this term here, and that becomes row D C naught, but sensitive to A naught. Our new sum of products equation becomes D C naught B naught, which is that term, or D B A, or D C naught A naught, or D naught B A. This is good, and it's certainly a move in the right direction, because now our circuit consists of 4 3-input AND gates and a single 4-input OR. But we have to ask ourselves, can we do better? That's a relatively easy question on these K-maps, because all we have to ask is, have we made the largest circle possible? For example, this is the BA column. We can also circle these 4 minterms here and describe that as the D C naught row, meaning our simplified equation becomes BA or D C naught, which is the best circuit we've seen so far, because all we need is an inverter, two input AND gates, and a 2-input OR gate. There's a few things you need to keep in mind about these circles. Keep them on the straight. That's up and down, as we've shown here, or left to right. Never on the diagonal. That does not work. We can circle a single minterm, 2 minterms, 4 minterms, or 8. Never 3, 5, 6, or 7. Of these, it's 6 that gets people in trouble the most. Here's a few examples to get you started. A function with 3 inputs and minterms 0, 2, 4, and 6. You could say we're selecting all of the even things. With 3 inputs, the Karnaugh map can take 2 different forms. It could be built this way, or it could be built this way. For the one on the left, inputs C, B, with A running on the top. For the right, it's input C with B, A running across the top. CB on the left can take numbers 0, 0, 0, 1, 1, 1, 1, 0, with A being 0 or 1. Here, BA can take on values 0, 0, 0, 1, 1, 1, 1, 0, with C taking on values 0 or 1. Let's go ahead and label the minterms, and then place a 0 or 1 based upon our original function here. So it does include minterm 0. It includes minterm 2, 4, and 6. Everything else becomes 0. And on the right, 0, 2, 4, and 6. The largest circle on the straight is here, which means F is equal to the A naught column. On the right, you might be tempted to circle these. And while that's true, there is a larger circle. Keep in mind that there's a 1-bit difference between these two here and a 1-bit difference between these two terms, which means we can circle this way. That is interpreted as the A naught column. So F again is equal to A naught. Here's another example with inputs DC and B and A. It's good to exercise your pen to learn where these numbers go. Even more important is to recognize where these minterms go. As far as the minterms are concerned, 0, 1, 3, 5, 7, 12, 11, and 10, with all others being 0. As your opening move, go ahead and circle these 4. Recognize that as the D naught row and the A column. The next thing we can circle are 10 and 11. Those exist in the D C naught row and a column identified as B. Minterm 0 can be covered this way, where that implicant is described as D naught C naught, and then in the B naught column. Finally, there's poor minterm 12. There's nothing adjacent to it, so we simply have to describe that as DC, B naught, A naught. Putting this all together, our optimized sum of products equation is D naught C naught B naught, or D naught A, or D C naught B, or D C B naught A naught. One more example. This is one of those fun K-maps because you get to circle the 4 corners. Those corners are described as C naught and A naught. As far as these 3 minterms are concerned, you could circle that way, or that way. Remember, you can't circle 3 minterms. It would have to be 2 or 4. So let's choose this circle and this circle. This piece is described as D, so that's the D rows, C naught column. This piece is described as the DC row with the A column. That sum of products equation is described as C naught A naught, or DC naught, or DC A. As we finish up, let's take a quick look at the Quine-McCluskey algorithm. As we finish up, let's take a look at that Quine-McCluskey algorithm. Keep in mind that our entire discussion has been about taking a sum of minterms equation, running it through some kind of minimization process, and finding an optimized sum of products equation. In all cases, this minimize process asked the same question. It asked single bit questions. For example, what is the difference between 1 and 3? In 4 bits, 1 would be described as D naught, C naught, B naught, A, and 3 would be described as D naught, C naught, B, A. The difference is the B term. So if we had minterms 1 and 3, we could describe it or simplify it as D naught, C naught, not interested in B, A, or simply D naught, C naught, A. That was a single bit comparison. That single bit was the entire foundation of the K-map, and it turns out it's the foundation of the Quine-McCluskey method as well. The difference being that the Quine-McCluskey is an algorithm based on tables, whereas the K-map was a simplified grid. In the end, both produce the optimized sum of products equations. With that said, let's jump right to an example. Let f equal the compact sum of minterms 0, 1, 7, 8, 9, 10, and 11. The 0 minterm can be described as 0, 0, 0, 0. The 1 minterm as 0, 0, 0, 1. 7 as 0, 1, 1, 1. 8, 9, 10, and finally 11 as 1, 0, 1, 1. The algorithm starts by asking a question. How many times does the number 1 occur in each minterm? For minterm 0, it never does, so we can put a 0 here. For minterm 1, there is a single 1. Minterm 7 has 3. 8 has 1, 9, 2, 10, 2, and 11 has 3. The next step of the algorithm is to group each minterm according to the number of ones contained in that minterm. There's a group with 0 ones. That would be minterm 0, where minterm 0 is described as 0, 0, 0, 0. There's the ones group, which would take care of minterms 1. So we're going to check these off as we go. And 8. 1 is described as 0, 0, 0, 1, whereas 8 is described as 1, 0, 0, 0. Group 2, which are things that contain 2 zeros. So that's 9 and 10. In group 3, we have 7 as 0, 1, 1, 1, and 11 as 1, 0, 1, 1. With everything in a neat table, we can now do comparisons, looking for single-bit differences. For example, we're going to compare minterms 0 and 1. Then we'll compare minterms 0 and 8. It's almost like algebra with the FOIL method, because the next thing we're going to do is compare 1 to 9, then 1 to 10, 8 to 9, and 8 to 10. Likewise, 9 to 7, 9 to 11, 10 to 7, and 10 to 11. Each time looking for a single bit difference. We start with group 0, where we compare minterms 0 and 1, where we find a 1-bit difference. That's recorded as minterms 0 and 1, with a difference on the least significant bit. We compare 0 to 8, where we find a 1-bit difference. That's recorded as 0, 8, x, 0, 0, 0. That takes care of group 0. Group 1, we compare these two, where we find a 1-bit difference. That's recorded as 1, 9, x, 0, 0, 1. 1 and 10 are compared, but we see there's multiple bit differences there, so we ignore it. 8 and 9, there's a 1-bit difference there. So 8, 9. That would be 1, 0, 0, x. And now 8 to 10, with a 1-bit difference there. Next is group 2. Comparing 9 and 7. Looks like we have multiple bit differences there. 9 to 11. That one's valid. So we'll record that as 9, 11, 1, 0, x, 1. 10 to 7. Multiple bits. And 10 to 11. Looks like a single bit change. That takes care of our conversions, but before we leave the table, we have to make sure that we've carried all of the minterms with us. So 0 certainly carried, 1, 8, right? You see 8 there. Actually, you see 8 in a bunch of different places. Let's see, 9, 10, but not 7. So we're going to circle that, and we're going to come back to it at some point. And the last one is 11. Okay, so that got carried. The good thing about this algorithm, it's very predictable. We made a table. We made comparisons within the table. Based on those comparisons, we made another table. We get to do the same thing all over again. Our next table starts with G0. We make comparisons like so, looking for single bit differences. Keeping in mind that they have to have x's in the same spots. So nothing here. This one is valid. We would record that as 0, 1, 8, 9 with x, 0, 0, x. Nothing here. How about here? Looks like there's a 1-bit difference there. So we'd record that as 0, 8, 1, 9 with x, 0, 0, x. Group 1. We make a comparison here. Nope. And here. No. Here. No. Here. Looks like there's a 1-bit shift there. So 8, 9, 10, 11, 1, 0, x, x. And finally, these two, that's recorded as 8, 10, 9, 11, 1, 0, x, x. Our last comparison is here with no match. Let's make sure we carried everything over. So here's the 0, 1 term, that was carried over. The 0, 8 was carried, 1, 9, 8, 9, 8, 10. There's 8 and 10, 9, 11, of course, and 10, 11. We could continue on, but I think we've gone far enough to see the pattern here. This becomes C0, B0, and this is D, C0. Putting everything together, our equation is C0, B0, or D, C0. Be careful. Let's not forget this. So minterm 7 is D0 CBA. And there you have it. That is the optimized equation. Just to make sure, let's go ahead and put this into a K-map. DCBA, minterm 0, 1, 2, 3. Our original equation was the compact sum of minterms 0, 1, 7, 8, 9, 10, and 11. 0, 1, 7, 8, 9, 10, 11. For our circles, we can grab these 4. That becomes D, C0. That's encouraging because that's that term there. There's minterm 7, which is off all by itself, as D0 CBA, which is that term. And finally, we have these, which are represented by C0, and it looks like we're in the B0. Mission complete. This compact sum of minterms is indeed equivalent to this sum of products. This was very easy to do using the K-map. In fact, it was so easy that if you look back at this Quine-McCluskey method, you might ask, why even bother? But there's something you need to know about K-maps. K-maps work very good when the number of inputs is limited. We were dealing with a 4-input system. Very easy to do. For systems with 5 inputs, the K-maps become 3-dimensional. With 6, 7, or 8 inputs, the K-maps become completely useless. However, the Quine-McCluskey method still works. It's tedious, but it works. It would work even better if you wrote a computer program to automate the process.